Hello and welcome to Toddcast number 21. This one we're going to talk about cyclic alkanes. So again, alkanes, no pi bonds, just everything is all sigma bonds. And then cyclic, meaning there has to be some sort of ring, at least one ring in the system. We're going to consider one-member ring or single ring systems. But cyclic alkanes could, in theory, have more than one. But we'll go ahead and start with just the basic idea of how you draw them. And it may seem trivial, but the way you draw structures becomes really important for recognizing how reactions are going to occur. Because molecules have to line up a certain way. So if drawn incorrectly, then you won't be able to predict how it's going to react. So I want to pay careful attention. So I want to start with the idea that our bond angles need to be 109.5. That's our going notion because everything is sp3 hybridized. That's what we're going to at least assume to be true. And as a consequence, it's going to be kind of hard to make some of the rings. So we'll have to figure out how this is going to work out. So if I have the bond angle here, if this thing closes up, if that structure forms where you have carbon here, and carbon here, that bond angle based on linear connectivity is only 60 degrees. So that is incredible ring strain, meaning three-membered rings, 6-degree angles, are highly unstable, and it really won't exist for very long. You can potentially make it, you can force it to happen by reacting things that are so unstable to begin with that it settles for a three-member ring, but that will be very, very reactive. Okay, so I want to consider two more angles of 109.5, 109.5. If this structure closes, those angles go down to 90. The one saving grace is it can pucker. It doesn't have to be planar, so it can act in such a way where this corner and this corner maybe go down a little. This one comes up, this comes up a little. So the angle can be made a little bit bigger, but even then it's not close to 109.5, but it is still better than 60. So this is still strained, but a little more stable. So we'll see a few more four-member rings naturally form. Five-member rings, 109.5 sounds great, but it ends up the angles are 108, because if you add up 108 times 5, you get 540. Total number of angles, if you remember, the number of sides minus 2 times 180. So 5 sides, so minus 2 would be 3. 3 times 180 would be 540. So this is how it's spread out. But again, there's nothing forcing it to be planar. So you can actually have one point contort either into the plane or out of the plane. And as a consequence, the angles can get closer to 109.5. So five-member rings, stable, you find them in nature. So good rule of thumb, almost never found in nature, highly unstable. Rarely found in nature, not very stable. Reasonably common in nature, fairly stable. And then finally, six-membered rings, absolutely the most stable of all, the most common we'll see. 120 is definitely not 109.5. So this is that case where actually when it folds into three-dimensional space, it can contort in a way where it actually can make the angles a little bit smaller. So it will contort and twist whatever way it can to try to adapt closer and closer to the 109.5. But if it can't get there, it can't get there. One piece of interest I want to point out is on the cyclopropane. If I draw my orbitals linear, that'd be one thing, but as it were, it ends up the orbitals are not linear. So I need to draw this a little bit bigger. I apologize. So the hybrid that it's using will look like that. And then, so let me color these lobes together, and these lobes together. I didn't do the greatest job drawing, but if I actually draw that line and that line, that's also how it can make the angle a little bit higher. It's still not going to make 109.5, but you end up having what they call bent bonds. Electron density is not collinear, it's off, but that also weakens the bond. You don't have as good an overlap. So therefore, again, they are not the most stable. Okay, so different types of strain. This is what's known as angle strain. This is a better picture of how those orbitals line up. So again, the angle is not quite as bad as 60, but it still is pretty tough. So cyclopropane exhibits what's known as angle strain, not getting close enough to 109.5. But then there's also something called torsional strain, where you have to look from the side to see this. So if I do a side view of this structure, the H's would be like this. So like we're talking about with the, sorry about this. So we're talking about with the Newman projection from last time, if they are eclipsed and these H's are all eclipsed, then you have issues. And so torsional strain, torquing something is turning it slightly. So if you rotate and torque a little bit, this H drops out of the plane, this drops out of the plane, the lower ones, it has a drive to twist. So it has both angle strain and torsional strain. The plane wants to rotate as best it can to contort to get those out of an eclipse conformation. With butane, it forms the so-called envelope structure. I don't know who came up with this, or well, puckered structure, I guess is the term they use. This puckered structure, but it's not quite planar. The H's, because this is slightly down, this is straight up, slightly down, and this is straight down, you don't get as much torsional strain. You don't have the, I guess, the gauche anti-interactions to worry about. So it has slight, like a little bit of angle strain, but you don't get torsional strain here. Where you get the torsional strain is here, here, and a little bit there. But you end up getting these two H's are directly in line and they want to rotate away from each other. So you end up with torsional strain from those H's, not the neighboring H. This is up, this is sticking out, this is down, but the bridging ones and then the bridging ones down there. Cyclopentane. This one, not so bad. You can kind of get away from the angle strain by the right folding. So it's kind of like this in plane, that one pointing up, if you will. But you end up with torsional strain. These are eclipsed and they don't want to be. So it's going to try to twist and turn on itself. So can contort to form this envelope structure, to eliminate angle strain or minimize angle strain at least. But the H's are eclipsed, so experiences some serious torsional strain. So it's not as bad as the other ones. That's why they're more common in bio. And that's going to be, again, our yardstick, because we see it in biological systems, then it must be reasonable, not terrible. Terrible. The six-membered ring is going to be the one we will focus on the most. It's going to be the most interesting. So the carbons are here. And so if I just consider the carbon ring system, all the angles can get really close to 109.5. And your H's ends up, these are far enough apart that they can interact, but they don't that much. They're called axial because they're on axis sticking straight up or straight down. And these that are along the perimeter, rather than call them perimeter H's, we call them equatorial. It ends up that if I look at it, so if I look at a Newman projection, say from here to here, so my eye is looking here and here. So if I'm looking that way, then that H here, what carbon's that one? This H is down, the one on back is down, and this one's up. Notice that these are far enough apart, so nothing is really running into each other. So it ends up, and then these H's, it looks kind of weird the way they're drawn, but they're coming down and out. So this is going into the page, this is coming out. So I should, even though we don't do this on this structure, I should emphasize that that's going back and into the page. Like that. So it ends up then, these don't interfere. So chair conformations, and somebody decided this is a chair. So if you have a recliner that might look something like this, that's your chair conformation. You're going to hear me use that a lot. You're going to hear O-chemist use it a lot. So it's going to contort into the so-called chair conformation to eliminate angle strain, and it ends up, it minimizes torsional strain. So six-membered rings are highly abundant in biological compounds because of the stability. So we're going to spend the bulk of our time doing chair conformations. And because it's so common, you really should learn to do it. So I'm going to do two ways. I'm going to do the artist rendition, and then for the artistically challenged, such as myself, a way you can also draw them. But for those who are artistically inclined, you start with a line slightly up and to the right. You can start up and to the left as well, but I'm going to choose up and to the right. And then you make a parallel line, same length, same angle, same orientation, a little bit further away. You're then going to draw two parallel lines as well. So this one's going to come down here. This one's going to come down there. Equal length as one another, parallel to one another. Angle should be the same here and here. And then you're going to connect the lines here with more parallel lines. So parallel line there, parallel line there. That is an accurately drawn chair conformation. For the substituents, every carbon has two groups coming off. I'm going to say H is at first. So that means I have 12 more lines to draw. So it ends up, our lines are going to continue to be parallel. So these two parallel lines will have a parallel line there and a parallel line there. And these two here will have a parallel line here and here. These two here have a parallel line here and here. And then that takes care of six. So we have the two parallel, and two parallel that make up the ring, the parallel, 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 and then make up six more. And then I have six more, three straight up, three straight down. So you'll notice if it intersects in a point, it's down. If it intersects in a point going up, it is up. Okay, so I want to keep track of my lines right now. So I'm going to color coordinate. I have a parallel line here and here. So those two, I have parallel lines here and here. I have parallel line here and here. I have three lines up here, three lines down, what's known as axial. So I need altogether 18 lines. So I have 12 drawn so far. So I'm going to take red ones and make them parallel here and here. Take blue ones, make them parallel here and here. And take green ones, make them parallel here and here. So we'll see how this pops in. So that one right there, those are parallel to the blue. Those right there are parallel to the green. And those right there are parallel to the red. So if you are highly artistic, you're going to end up with four parallel lines, and four parallel lines that'll cover the ring and then the equatorial constituents. And you're going to have three axial pointing up from the point up intersections and three axial downs from the point down. So altogether 18 lines, three sets of four parallel lines to make the ring and equatorials, three axial up, three axial downs. For the coordination challenged, that would be me. Draw two parallel lines, slightly offset, can be offset at left or right, makes no difference. And then add a point. This one's sticking out, put a point up here. This one's sticking out, put a point down there. So I'm going to put two dots. And then I'm just going to play connect the dot. Connect the dot there, connect the dot there, connect the dot there, and connect the dot there. It is not as pretty. Absolutely, positively, this structure is not as pretty as this one. Plus, this is colorful and beautiful as well, but just based on the drawing, but this works. Axials, I'm going to draw those first. So axial up at that point, axial down at that point. Axial up at that point. Axial down. Axial up. Axial down alternates. So point up, point down, down. Point up, point down, point up, point down. Then we're going to have that same scenario where we have 109 angle. So I'm going to draw that 109 there, 109 there. Going to draw 109 there, 109 there. And I'm going to draw 109 here and 109 here. So lo and behold, I actually was able to draw it reasonably well. This still will show what you need, but it won't create artistic challenges quite to the same level as this. So hopefully this seems reasonable. Okay, so there's my axial lines up. There's my axial line down. There are my equatorials. There are my equatorials. There are my equatorials. Oh, shoot. My red lines, I just knew it looked kind of ugly. Because I apologize. I was looking at this structure, which is point down and point up. This is point up and point down, so they have to invert. My apologies. Okay, so we have different ways to draw it. So now that we have it drawn, now that you have practiced thousands and thousands of these over the last 8 seconds, let's go ahead and again look at the ring system. So here's my carbon 1, let's say 2, 3, 4, 5, 6, or carbon 1, 2, 3, 4, 5, 6, or carbon 1, 2, 3, 4, 5, 6, whatever way you number it, 6 in a ring. Point here in the ring, so axial up, and axial up. So it goes axial up, down, down, up, down. So important to recognize that. So if this group is down and it's on the equator, so my axial ones point straight up or straight down. Actually, let me color coordinate the same way I did earlier. So those are my axial straight up or axial straight down. If it's not axial up or axial down, then it is equatorial. Everything can be described by equatorial or axial. Every carbon has an axial and an equatorial, equatorial and axial, axial and equatorial, axial and equatorial, equatorial and axial. They all have one of each, and one is going up and one is going down, but not necessarily the same. So equatorial down here, this one's equatorial. It's on the equator, sort of, but it will be equatorial and up. Axial up on this one, axial down. So if this is axial down, this must be equatorial up. I move one over. So if I go from this carbon, axial is now up. Equatorial's down. We go over here, axial's down, equatorial's up. Over one carbon, equatorial down, axial up. So it alternates as you go around. So let me get rid of my circles. And this is one of those things you will absolutely have to recognize. So up and down, there's 3 downs, down here, and down here, and 3 ups. And there are 3 axial ups, 3 axial downs. And so equatorial down, equatorial up, equatorial down, equatorial up. It alternates as you go around. Getting used to this is the hardest part. So drawing it takes its toll, but once you have it drawn, recognizing where things are. So to flip a chair, this is where a model will help immensely. But I'm going to arbitrarily label this as carbon number 1. A chair, like various structures, is free to move in some way. So when there's no ring, things can rotate around sigma bonds. When there's a ring, they're limited. They can't rotate, but they can contort and twist. So this twists up, and this one twists down. Then you'll notice this one is now point up. This one is now point down. So the ring has flipped from one chair conformation to another chair conformation. So this might be the feet on the left, head on the right chair. This is now head on the left, feet on the right chair conformation. So it flipped. In doing so, I want to just pay attention to this one. This one here was equatorial and up. Now that one is still up. So up stays up, down stays down. But when you flip, equatorial becomes axial, axial becomes equatorial. This group right here was axial and down. It is still down. Up, down doesn't change, but now it turned into equatorial. This is kind of cool when you look at it with models. So definitely want to go through the model kit and twist these things around. Okay, I'm going to erase what I've drawn and toss in the computer generated. So still want to put in, this is carbon 1. Carbon 1 will be found over there. This is carbon 4, let's say. It'll be found down here. So down and down yellow, up green. This will be up yellow, down green. So it gets there by this moving up a little bit, this one moving down, this one moving up, that one moving down, this one up, this one down. So if I consider some substituent X on this right here, it is up and is equatorial. It is next to the green. So if I go 1 away from the green and 2 away from the yellow, that's the carbon. And X still has to be up. So if I draw it in, X, up, and up. Up doesn't change, but what does change is it went from equatorial to axial. Okay, so it's up and equatorial. So I'm going to draw the blue circle to emphasize the carbons next to the green and 2 away from the yellow. So there's that. So it is still up. Up stays up, but it is now axial up. When you ring flip, you can contort. Meaning, a cyclohexane structure, a molecule that has a 6-membered ring in it, can contort to form the most stable conformation possible. Okay, so let's consider this red carbon. It is 1 away from the yellow and 2 away from the green. So 1 away from the yellow and 2 away from the green, we'll put it right here. So if I have some substituent, let's say Z, is equatorial and is down. So over here, it's going to stay down, but it's now down but axial. So again, when you ring flip, you change all the equatorial to axial, all the axial to equatorial, but down remains down, up remains up. You cannot change up and down unless you break the bonds, take them off the structure. Okay, so this applies to a question. A monosubstituted cyclohexane has 2 possible chair conformations. Consider methyl cyclohexane shown below. So here's my 6-membered ring, here's my methyl, here's my H. Are the 2 chair conformations degenerate? Okay, so let's figure out what that means. So I'm going to draw my chair conformation. And I'm going to arbitrarily call this carbon, this one right here, for visibility's sake. I'm going to draw my CH3 up and my H down because CH3 is up, H is down. If I ring flip it, so the 2 structures, I'm going to draw it like that for now. This is point up on the left, point down on the right. So if I redraw it where it's point down on the left and point up on the right, then this carbon right here just became this carbon. And because it's point up, equatorial will be, or axial will be up, equatorial will be down. The CH3 is still up. So the H is now down. So we have to decide, are they degenerate? Meaning, are they of equal energy? Nope, because axial can run into other groups. Axial can run into the other 2 H's. So those 3 can all interfere. Equatorial is a little more stable. So axial is less favorable. So if I were to redraw these equilibrium arrows, I would show it like this. So I would emphasize with my arrow that it would much rather go back to equatorial as opposed to axial. Okay, find a view of the carbon with constituents on a Newman projection. So I've drawn this structure. So time to draw a Newman. So I'm going to erase everything. So there's my chair conformation. It's up and axial. Another one equatorial and up, so still up. There's my carbon of interest. So far, so good. So that's just what I drew down here, but now computer generated is much prettier. For the Newman projection, you're actually going to be looking down 2 carbon-carbon bonds simultaneously. So you're going to have a dot here, circle here, dot here, circle there. So let me go back to this, sorry. So if I'm going to only draw this one. So on this, I have an H and H in the rest of the chain. So I'm going to have a dot with a circle in back. Coming off it, I'm going to have that H, and the structure itself. On the back carbon, I'm going to have an H and an H. Okay. On this carbon here, I'm going to have another dot, another circle. So that's this connection right there. I'm also going to have an H and an H on front. On the back, I have my CH3 up and my H there. And I have third bond going up like this and a third bond coming back like that. And then I'm going to put the H's like this. So those don't really do justice in this drawing, but there is my so-called Newman projection where I have two carbon-carbon bonds simultaneous. It is very, very ugly. And just want to emphasize that this part we don't care about, but this we do care about. So for this one, I drew the axial. So axial, those two can run into each other. Okay. Fill all assumed H's on the Newman carbons, then go ahead and draw it. So here it is again. Going to hopefully have a computer generated version now to cover up my bad drawing. But again, this one here, this front one is there and there. So let me do this in red. And then this one I'll do in red as well. I'm going to do the back one in green. And then notice here, didn't even bother putting those other H's in there, just focused on that group there. So these bulky groups are gauche. Whereas if I draw the other version with the equatorial, again, let me just emphasize these are here and here. These are here and here. Here and here. Here and here. And then this is in back. This is in front. Now it is anti to the rest of the chain and it's staggered. So it works out well for me. So the gauche interactions between the R groups here are tough. The anti-orientation makes it a little bit more stable. So equatorial, more stable than axial. Okay, so that's going to be your take-home message. Let me just emphasize that by saying equatorial, when all things are equivalent, as far as substituents go, you would rather have a group equatorial than axial. Okay, so equatorial is more stable. Hopefully that makes sense. This was, again, a tough one. You have to learn how to draw Newman projections of cyclohexane and chair conformations of cyclohexane. And you have to identify equatorial axial up and down, keeping in mind when it ring flips, up stays up, down stays down, but equatorial and axial interconvert. And as you go around the six-member ring, axial is up on one carbon, the neighboring one will be axial down. Conversely, if equatorial is down on one carbon, the neighboring carbon, equatorial will be up. It will come in time. It is not one of the easier topics we will do, but in time you'll get it and it'll be second nature. So, as always, hopefully this Toddcast went well, and I will see you in the next Toddcast. Bye.